Hello, my name is John Madden. I'm Director of Facilities Management for Water Company. You're all very welcome here today for a kind of presentation on the introduction to infrared thermography. Our speaker today is John Magna, Director of Irish Thermography Solutions Limited. John is a certified thermographer, PEO assessor, and has over 35 years experience in building management trade. Pass it across to John.
Thanks very much. Good afternoon. Yes, my name's John Magna. The introduction to infrared thermography and its use for facilities management. The part of this presentation is very much focused on an introduction to infrared thermography. If you're aware of what infrared thermography is and what it can do, you can apply it in all kinds of ways. You may well find other uses that currently aren't being explored for thermography. Infrared, it's a form of energy, part of the electromagnetic spectrum. Electromagnetic spectrum goes all the way from gamma rays right the way through to radio waves. Visible spectrum is a very small part of that, and infrared is just outside of the visible spectrum. It's similar to the visible spectrum in a lot of ways. It's not normally visible to the human eye. There is a slight crossover between the visible and the infrared in what we call the near infrared. There are certain temperatures that we can actually see radiating infrared. The type of instruments that we use nowadays are operating in this part of the infrared spectrum, somewhere between 2.5 and 14 microns. Infrared, all objects above absolute zero emit infrared radiation. So if we have a device that's calibrated within certain temperatures, so at certain temperature ranges, we can record the infrared radiation that's being emitted from those objects. The amount that's emitted from those objects depends very much on the object's temperature, but also on its surface condition. And all objects above absolute zero is 0 Kelvin, minus 273.15 degrees centigrade. It's the point at which all vibrational kinetic energy would cease. All objects above absolute zero have vibrational energy. All the molecules in the room, all the molecules around us are all vibrating. And the temperature that those molecules are at is a function of that vibrational energy. The faster those molecules vibrate, the higher the temperature. And the faster they vibrate, the more infrared radiation they emit. So infrared cameras, or thermal imagers, enable us to detect that energy and convert it from a part of the infrared spectrum into the visible spectrum. We can now see quite plainly there's air leakage around the sockets and there's air leakage at the base of the wall. We can even see the stud work, we can see the fixings that have attached the plasterboard to the stud work. We need to have a temperature difference. For infrared thermography to work, we have to have a temperature difference, what we call a delta T. We need some form of heat transfer to be taking place. What we can do with an infrared camera is generate a two-dimensional thermal density map. Whatever we point the camera at, it will then give us very useful information about that object. And it could be anything. It could be a building, it could be a piece of equipment, machinery. We even have infrared cameras pointing out into space. We can now create a two-dimensional infrared map, thermal density map of whatever we're looking at. When we talk about thermography, what we mean is it's a non-destructive technique. It's non-contact. We're not having to disassemble something to find out about that object. Non-contact mapping and analysis of the thermal patterns that are being emitted from the surface of an object. People very often, when you turn up with an infrared camera and you're looking for an underfloor heating leak, and they say, how far down into the ground will the camera see? Well, the answer is it doesn't. It's only seeing the first surface molecular layer of most materials. But because of the nature of heat transfer, we can find a heating pipework leak because of that energy being conducted through to the surface. And the analysis part of it it's all very easy to generate an infrared image. Cameras nowadays are very easy to use, almost point and shoot. But you need to be able to analyse those patterns if you're going to make sense of that image. And images are open to interpretation. So thermography is that ability to be able to capture an image but also analyse it to find information about that object. So we say, well, what's a thermographer? A thermographer is a qualified individual, somebody who is capable of using that equipment, firstly to capture the image, but then with sufficient theoretical knowledge to analyse the data that's contained in that image. There'll be elements of image manipulation that may have to be taken into account, accounting for the differing emissivities of materials, which we'll look at further on. Qualified individual. As I said, modern cameras are very easy to use. You can pick the thing up, turn it on, point it at something, and they auto-range. As soon as you point the camera at something, it will look for the highest and lowest energy levels in that scene, and it will set itself to those energy levels, and it will give you an image. Very little instruction in terms of usage. If you buy a camera, a couple of hours with the salesperson will have you up and running. But typically, you need a one-day course to understand the basics and become familiar with the camera. If you want to go further with qualification, then you need to attend courses. I'm a trainer for the Infrared Institute. These guys on the bottom, it's a global company. And I train here in Ireland, I train in the UK, and next week I'm training in Dubai. We train all over the world, teaching people how to use infrared cameras, because the applications for infrared thermography are vast. You need to pass examinations and then you submit reports for review. And there's different levels. There's two schemes, two certification schemes, and they both offer 3 levels of certification. We have ASNT, the American Society of Non-Destructive Testing. It's been around for a long time. And we also have BINDIT, the British Institute of Non-Destructive Testing. The only difference between the two schemes is the way in which they certify. In both cases, they have the levels are exactly the same. So level 1, we're assuming that the thermographer has got sufficient skill and experience. They know how to use the camera. They can capture a good image, and they can take into account any environmental data that may need to be recorded to attach with that image. Because if you don't have the environmental data with an image, if somebody presents you with an infrared image, that's all it is. It's just a picture. So unless you have the environmental data that goes with that to explain what was occurring at that time in terms of weather conditions, if you're doing electrical survey, what was the load conditions at the time of survey? So level 1, able to acquire a good image and record any data. And then we talk about level 2, in addition to the same skills that level 1 thermographer will have, they're going to mentor a level 1 thermographer, but they're also going to have application knowledge and experience. Because now you're talking about analysing those images and determining whether or not it is a fault condition. Often we can look at images and we're explaining it away. We can see an anomaly, but there's a reason for it. And so it's not a fault condition. And also you might be expected to comment as to the severity. So again, if you're doing electrical surveying, does it need immediate attention? Or can we wait for the next planned shutdown? And then level 3, in addition to level 1 and 2, a level 3 thermographer would set up and administer thermographic programs. And again, would be aware of current health and safety regulations, government regulations, these type of things. And at level 3, you would be expected to contribute towards standards writing with regards to procedures. I'm actually a level 2 certified to do electrical and building inspections, but I was also asked if I would do an inspection on a wind turbine. Well, that needed a specific method statement to be written for that. You would expect a level 3 thermographer to do that, not a level 1 or a level 2. ASNT, American Society of Non-Destructive Testing. It's a second-party accreditation scheme. What that means is that the organisation that's carrying out the training organisation can also certify the individual. The coursework is exactly the same whether you go for certification for ASNT or BINDT, British Institute of Non-Destructive Testing. But that's a third-party accreditation scheme. What it means is you train with the same organisation, but BINDIT set the examination, and they certify that individual under what they call their PCN scheme. Now, it doesn't really make a lot of difference which scheme you go with. Globally, there are more thermographers certified with the American Society of Non-Destructive Testing, which is a historical thing. It's been around for a lot longer. But some companies are looking for ISO 9001 certification, quality management scheme. There's often a requirement that surveys are carried out by a minimum level 2 thermographer, and often it will specify a minimum level 2 PCN certified thermographer. So when we're looking at possibly yearly sign-off for electrical installations, they may well specify a level 2 thermographer. And they may specify PCN, or for BREEAM sign-off on new builds, again, they may well be looking for a level 2 PCN thermographer. And so why use infrared? Well, when you think about it, temperature is the most often used measurement. If we have a cold, the first thing we do is we put a thermometer under our tongue or in our ear or whatever. And if we know the temperature of an object, it can give us useful information about that condition of that object. So this is a topical slide in as much as we're talking about the Ebola virus. Well, we've had viral screening at airports for a number of years. You don't necessarily know you're being screened as you pass through the airport, but there'll be a camera set up with an automated system that's looking for elevated temperatures in this kind of region. Because if you've a viral infection, then typically you're going to have an elevated temperature across your forehead. Totally automated system. That's been around for some time. We've all travelled here today by some form of transport. It may be in a bus, it may be a car, a bicycle, we may have come on a horse, or we may have walked. But whatever form of transport we've used, if we look at that object in infrared, we can get a useful indication of the condition of that object. If it's a bicycle, are the brakes binding a little bit? What are the bearings like? Do they need greasing up? The same as if it was a car. If we're looking at bodies, our own body, it should be in symmetry. And if we look at a body and we find there's some kind of asymmetry, then there's got to be a reason for it. Typically those imbalances will show up as a temperature difference. So the possibilities for using infrared are huge, and the applications for infrared across the globe are endless. And again, why use infrared? Because we can use a thermometer. We can use a contact device. Infrared is non-contact. When you put a probe of something in contact with an object, you are actually altering the temperature of that object. When you put a thermometer in, or your mother put a thermometer under your tongue and say you have to wait a minute, it's for the bulb of the thermometer and the temperature, your core temperature, to reach what we call thermal equilibrium. But one may have started off at a different temperature to the other, so it will affect it. Admittedly not to a large degree in that particular instance. And again, we have thermocouples. But they're contact devices. If you've got a non-contact device, it now opens up a lot more possibilities. And again, being able to generate that thermal density map, we're not now just looking at a single point where we place the thermometer. We can look at the whole of the wall, or in this case, the whole of a termination box. And because we're looking at it infrared, and because the image has been what we call thermally focused, we can see where the highest energy level is. And we can see the energy tailing off down the conductor. So we know that that's going to be a conduction issue. It's a bit like if you put a poker into the fire. Eventually the heat would transfer from the end of the poker right the way through to the handle. It's conduction. And what we're doing as thermographers is we're looking for patterns, and we're analysing patterns. And the sort of pattern that you get from heat transfer from conduction is very different from the pattern you would get from convection or from radiation. So we're looking at patterns and we're analysing the images that we're presented with. We couldn't do that any other way. The other benefit of infrared is it's very quick. You can scan a room very, very quickly with a camera. You couldn't do that in any other way. You couldn't gain that kind of level of information in any other way than using an infrared camera. And again, the benefits, well, safety. You can't put a thermocouple or a thermometer onto a piece of rotating equipment or an energized system, an electrical system. You can't image or you can't record the temperature from a moving object or something that's changing in temperature. Sometimes in thermography we might activate that object. We might energize it in some way and see how does the energy move through that object. And then we've opened up even more applications. We can look at the tail sections of aircraft to see if there's any voids in there that may trap water and ice. Or we can use the same principle, which is thermal capacitance, to look for problems with flat roofs. Insulation that's retaining moisture for some reason. In that particular case, we use the sun to energize the structure. And then we watch it over a period of time and we see how that energy moves through it, because thermal energy will move through different materials at different rates and in different ways. We can record video of changes of temperature, which again is very useful. The survey that I did in the wind turbine, we set a camera up and recorded the splices coming down from the wind turbine over a 24-hour period. So we could see, as the turbine ramped up to full load, we could see how the temperature changed on those splices. You couldn't do that any other way. So safety is paramount. Remote, we don't have to physically be in contact with something. I could be imaging something at the other end of the room quite successfully if I have the right kind of lens and the right type of camera. And again, non-intrusive. They've come a long way in 40 years. In 2014, this is the type of thing you might have, modern camera. That's actually 1974, 40 years. And you've got the screen here, this is the camera, here's the electronics, this is the recording device, and here's the battery pack, totally laden down. But a portable device nonetheless. And facilities companies, or certainly electrical distribution networks, started using infrared because it's a very good way of looking at high voltage distribution systems. It's the only real safe way of looking at those kind of systems and looking at those kind of connections. With most things, with thermography, what you're looking at first is joints and connections. Whatever form of thermography it is, the weaknesses are generally in the joints. Connections, changes of material, changes of direction, whether it's buildings, whether it's electrical, whether it's mechanical, or whether it's the human body. Because that's generally where the wear is, at the interface. So nowadays, cameras are very portable, very easy to operate, and much more lightweight. You wouldn't have used that type of camera there all day without getting severe fatigue. Nowadays, you can literally hold that thing all day. Battery power will last you probably 4 to 6 hours on one battery. But in addition to understanding how the camera works, and that's fundamental, in a day's course all you would really learn is how does the camera work. You need to have a bit of an understanding of the physics behind the technology. And if you have that in conjunction with good camera usage, then you can use that camera for all kinds of applications. You're only then limited by your own imagination. If you have the basics, you can go into any situation with the same camera and gain very useful information as to what's going on. What happens is the camera gathers and focuses photons of infrared energy onto the detector, which is what we call a focal plane array. If you imagine, you may have done it, I certainly did when I was a youngster, you'd get a magnifying glass. And you'd be out in the sunshine and you'd set fire to something with the magnifying glass. Because what you've done now is focus the rays of the sun through that lens onto the piece of paper or whatever it happens to be. That's then the focal plane. That's the focal length of that lens. Whatever distance that you held that magnifying glass away from the paper or whatever it was, that was the focal length of that lens. And so we construct the cameras so that they focus all of that energy onto a detector, which we call a focal plane array. And it's a bit like a digital camera. The number of pixels on that digital array depends on, is what determines its resolution. The greater the number of pixels, the higher the resolution of the image that you're going to get. And the higher the resolution of the image, the more information you can gain from that image. And the more accuracy you can have if you're actually recording temperature, or you need to evaluate what the temperature is. Each one of those pixels actually has the capability of resolving detail and recording a temperature value. Now it appears when we do it in the camera that because we can see an image that somehow it's recording an image, but what it's doing is it's recording differences in energy levels. It's just a series of numbers, and then it's converting that into an image onto the screen for us. If you're specifying a camera, if you need a camera for a specific purpose, then one of the first things you consider is what's the number of pixels. Well, a 320 by 240 camera, which is a fairly common type of camera, it's not the highest resolution, but it's a fairly common type of camera. 320 by 220 will give you 76,800 pixels, each one capable of resolving detail, each one capable of measurement. 160 by 120, now you're down to 19,200, and again 120 by 96, 11,500. You can see the difference that it makes. And if you're up close and personal, if you're only looking in panels for electrical, then often the cameras are very low resolution and they're a fixed focus, but that's really all you can use it for. The other thing is the angle of the lens. Well, the ability to actually record that temperature or accurately measure it is going to depend on the number of pixels, but also the distance you are. And obviously the choice of angle is going to make a difference there. Wide angle, the target's actually at some distance. We may not be able to resolve detail on it. And standard lens, obviously it's bringing us that much closer, or you may require a telephoto. If you're doing external surveys on power distribution, then you probably would want a telephoto lens. You don't want to get that close to an object. But for most applications, the standard lens would be fine. What the electronics do is it takes that energy and converts it into a visible image, either onto an LCD screen or can send it via a cable, or wirelessly. Nowadays you can get an iPhone and an application for an iPhone that will connect wirelessly to the camera which I have there, which is a FLIR camera. Other manufacturers do the same thing, where it will connect. You could have with an iPhone or with an iPad. And very often then you can manipulate the image within the iPhone or the iPad, and if it's an iPhone, you could then send a very quick report if you needed to via that mobile phone. You don't have to go back and load it into software in a computer. What the electronics also does is it monitors the internal temperature of the camera. It keeps providing a reference point, because as you put more energy, focus more energy onto that detector, it gets hotter. And so it has what we call a Stirling engine, a miniature Stirling engine inside it, which actually cools the detector down. And so it's constantly going through this kind of recalibration process, a resetting device. And then depending on what you put into it, you have to put certain data into the camera, then it will provide accurate temperature measurement as well. So there's microprocessors built into the camera as well. The amount of infrared energy that's emitted from an object, as I say, it's a function of its temperature, it's a function of its surface condition, but it's also a function of the material that it's constructed from. And no object emits 100% of its energy in the form of infrared, or its thermal energy in the form of infrared. So they're only 13 mil bolted connections, and it appears that there's a temperature variation over that. But in fact, it's all at the same temperature. And what a lot of thermographers do if they don't have training is they'll look at an image like that and assume that there's temperature variation in there when there isn't. That's down to changes in emissivity. And unfortunately, metal components have very low emissivity, and they reflect of a lot of the background. So in this particular case, that area there, which appears to be much colder, 20.8 degrees there, is actually reflecting the background temperature of the area in which it's in. The highest temperature that's being recorded there, which is 42, is more likely the actual temperature of all of that connection. But differences in emissivity can cause false readings or false anomalies, which you need to account for. So as a thermographer, you have to know the fact that the total energy that the camera is receiving is not just coming from the surface. Some of it will be emitted, depending on the emissivity of the object, but some's going to be reflected. And that's going to come from the surroundings. Potentially some of it may be transmitted. Some materials will allow infrared to pass through, but very few. The lens of the camera is not glass. The wavelength of the cameras that we use won't allow infrared to pass through glass. So we calibrate our instruments to something that is called a black body. If it could emit 100%, it would be what we call a black body. And somebody called Kirchhoff determined that an object's ability to emit is the same as its body, absorb is the same as the body's ability to emit. So we have a reference, we have something that's 100%, and it's a constant. But only that theoretical black body emits 100%. All other objects are only emitting a percentage. We have grey bodies and we have real bodies. Grey bodies are constant, so black electrical tape or vinyl, if you take a reading from that, it will give you a fixed emissivity, and it's a good emitter. But most metals are real bodies and they're poor emitters. And the amount that they emit is going to change with temperature, wavelength and surface condition. Good emitters, poor reflectors, poor emitters, good reflectors. So if we're dealing with highly reflective surfaces in infrared, then we have to, the correction factors that we have to put into the camera are much more complicated. So typically you want to look for high emissivity. The good news is for building inspections, most building materials are a high emissivity and they're grey body. The problem then comes when you start looking at electrical installations, because now you're dealing with reflective surfaces, metallic surfaces. And often what happens when thermographers start doing electrical surveying of panels and they open the panel up and they'll see a hot spot and assume that it's a problem. It may just be a reflection of themselves. They may well be the highest energy source in that image, because a piece of bus bar will pick up your reflection. So we have to be aware of those kind of things. We need to correct for emissivity, reflective background, transmissivity, the amount of losses through objects that do allow some infrared to pass through, and environmental conditions. If you're looking at something outside, a connection on a power supply coming into a building on the outside, or some kind of connection on a distribution system, and it's windy and it's in the winter, you're going to get a totally different reading than if it's in the summer on a still day. So we have to account for environmental conditions if we want to know whether it's a fault condition, and if we want to get accurate temperature readings from the camera. We can get accurate readings, but we have to account for those variables. And then we put our images into a software program, and we can do various things to that image. We can maximize the thermal detail in what we call thermal focus. We can make adjustments for emissivity and the environment. We can put those kind of factors in. The thermally focus, what we're doing is trying to put as many colours available to us on the target so we can isolate the background. We can isolate areas that we don't need. We can change the colour palette. The colours aren't fixed. We can change those. And we can put measurement temperature devices onto the image so that we can get accurate readings from it. So typically you might be assigning some kind of severity criteria. If it's an electrical installation, we could put notes, comments, trend data, if it's something that we're looking at over a period of time. Generate templates for specific purposes, and we produce our reports. All of these images are all at the same temperature. That's in the visible spectrum. And they're all the same. The only thing that's changed is the palette choice. And different people may have different requirements. A lot of electrical thermography is still done in iron bow because that's the first palette we had available to us. But nowadays people tend to go perhaps more for a high contrast palette. It shows a little bit more detail. If you're looking at buildings, very often that's a better palette to choose. And again, if you're looking for leak finding, again, that's possibly a better palette to choose. But they all contain the same information, it's just how you present it. And in the software, you can go in and you can change all of that. Here's all the information that's embedded with the information, the time and date of when that image was taken. The camera, the serial number of camera, all of that information is embedded in the image. When we thermally focus the image and choose our color palette, again, they're all the same. All we've done is change the color palette and then modify the image, change the level and span to hone in on where is the actual highest energy level here. So with that image there, we can see exactly where the highest energy level is. And we can see again that it's a connection issue. Various options are available to us. We can put spot functions, area functions, etc. Delta T we're always looking for. If you're looking for a problem, certainly with electrical, you need to refer it back to something. You need a reference temperature. And similarly with buildings, very often, if you're looking to see if there are inconsistencies in the structure, you might be looking for a temperature difference. So we talk about delta T, temperature difference. And occasionally you might put line profiles on. Again, the same image with the line thrown across those 3 points. We can now see it graphically demonstrated, the profiles of the temperature across that line. Or we can put an area in and it'll give us an average and a maximum and a minimum. Different ways of presenting it, but how you put that into a report depends very much on the client needs. Obviously the report's got to be easy to interpret and contain all the relevant information and any reasoning behind the comments that you might make. Most software is going to have general templates that you can use, but you probably want to set your own up with your own logos on there and your own information. And at the end of the day, very often the easiest thing is to just cut and paste images into a Microsoft Word or some kind of word processing program and develop your reports that way. With facilities management, there's lots of opportunities for using infrared. Building fabric inspections, energy loss, leak finding, typically water leaks, but it can be other things as well. But more often we're looking for water leaks. We can look at electrical systems, mechanical, hydraulic, and heating and ventilation systems. Obviously, over time, all fabric deteriorates. Any structure is going to deteriorate over time. We can look for delamination and spalling of facades. We can look for voids behind plaster or render surfaces. We can use it for roads and tunnels and bridges, exactly the same techniques. Flat roof leak detection, if we're finding areas with a flat roof that over a period of time have failed. We can find them using infrared very quickly and very easily. Moisture penetration, problems where moisture is coming into the building. We can also look for trapped moisture, where moisture is actually passing out through the structure, becoming trapped somewhere within the structure, becoming interstitial. You get interstitial condensation, you've a lot of problems potentially with that structure, especially with some of the modern materials that we use, some of the lighter building materials we use nowadays. If you get interstitial condensation, it can lead to all kinds of problems. We can look for air leakage. And with building energy loss, if you can identify where the energy loss is from that structure, it's very often the first step in reducing energy costs. And nowadays, we're all very concerned about reducing energy costs. If anybody goes down to look for 50,001 energy management system, then it's very much focused on reducing energy. Infrared can play a very important part in that. And the cost, reducing the cost for heating and cooling. On a large scale, certainly on bigger buildings, but also on domestic as well. We can now find areas within the structure where there's a possibility of mold growth to develop. We can look for areas of the structure where there's inconsistencies in the insulation, or there's unwanted air leakage that are now causing occupier discomfort, and again increased fuel bills and increased risk of that structure deteriorating over a period of time. Again, very quick and very easy. That type of surveying is very rapid using an infrared camera. For leak finding, it's a very quick and accurate method of locating underfloor leaks. And again, you couldn't do it any other way. And you can pinpoint within probably 50 80 millimetres where that leak actually is. And again, it could be some distance under the floor. Community heating system. That particular leak was 500 millimetres under the ground. And yet it showed up very readily using infrared thermography. Admittedly, you have to get the right conditions. You need to get the greatest amount of temperature difference. So in that instance, we put the heating system up as high as we could. And I went essentially very early in the morning. Building thermography is a bit of an antisocial occupation, because typically you're working when it's cold outside and you're outside. You want a good temperature difference. So you want the building, the structure to be heated, and you want a low temperature outside to maximize the temperature difference. But very effective. With electrical systems, obviously thermography can provide information on the entire system. Everything from generation, transmission, distribution, all the way down to the plus or minus 5 degrees that you would have in a laptop. You can use thermography and find useful information about that object or that circuit. Obviously, we need a current flowing, and in an ideal world, when we're doing electrical serving, there'll be at least 60% load. Normal conditions, but at least a 60% load, because obviously as the load increases, then the temperature is going to increase. And very often nowadays, we're looking for electrical surveys for a yearly sign-off on buildings. Some insurance companies will offer discounts if you have a yearly sign-off on your electrical installation. Or it may actually be a requirement for continued insurance cover that you have yearly sign-off on your installation, because insurance companies realise that thermography is actually a very powerful tool when it comes to looking at electrical systems. It's very effective and it's very accurate. It says there, may well be looking for yearly sign-off. What you're doing is you're producing a report where you look at every panel. And now you can demonstrate that on that day and at that time and under those conditions there were no problems. You may well find problems when you do a yearly sign-off inspection. It's not uncommon to find problems. Well, obviously then the insurance company might say you need to address that before the insurance cover is back in place. Could work against you. But again, very effective. Thermography is very quick and very effective. And regular inspections could prevent failures. We use thermography as part of predictive maintenance programs. So we can analyze the condition of a system by looking at the temperature of various components within that system. And obviously the electrical system is very much part and parcel of that. And prevent costly failures. Nobody wants an unplanned shutdown, especially if it's manufacturing. You want to schedule your shutdowns and you want to schedule your maintenance accordingly. Unplanned shutdowns are very costly. And obviously we can also look at mechanical systems, hydraulic systems. Anything is going to, generally speaking, show an increase in temperature as a fault condition develops. So if you trend something, if you monitor it over a period of time, and it could be a very quick once round on a regular basis with the camera, you can see if there's any changes. You have to have a baseline, you have to start from somewhere. But now when you go back to that piece of equipment each time, you can get an indication of the health of that component or that whatever it happens to be, motors, bearings, pulleys, etc. Generally speaking, they will always show an increase in temperature as they start to fail. Infrared, very, very quick inspection technique. And so very often we, as we say, you trend systems. It can be very cost effective as part of a preventative maintenance program. Admittedly, there's going to be an investment in a camera, an investment in some form of training. But the potential savings are huge if you can avoid unplanned shutdowns. And then obviously with heating systems and ventilation systems, balancing, looking for primary heat loss that isn't accounted for in the calculation. In other words, we want to deliver heat into this room, but maybe there's pipework that's running back to the boiler or the distribution system. That may well be primary heat loss if it's going through a void that's somehow connected to the outside. That could well be primary heat loss. or from a boiler system in a house where the boiler is actually outside. Primary heat loss before that energy is actually delivered where you want it inside the house. We can look for pipe placement, certainly with underfloor heating. And I've done surveys of that type of thing where somebody's wanted to drill into the floor and there's underfloor heating and they don't know where the pipes are. Well, you can map it out quite plainly. You can find leaks very effectively in underfloor heating systems. And also, thermography is really the only way of accurately balancing an underfloor heating system. Generally speaking, they're just balanced with flows on the manifold. But my experience is that that's never fully effective. But if you put thermography into the mix, you can actually accurately balance the system and find out if things are actually connected in the way that they should be. And very often they're not. You've got thermostats trying to control the wrong zones. Again, you'll find that using thermography. And again, air leakage. Discomfort, potential for problems with the building fabric, and general increase in energy use as a result of unplanned air leakage. So that's only really a basic understanding of thermography and what it can do, but I'm quite happy to take any questions if anybody's got any regarding thermography generally or specifically for buildings. And the room is silent. For glass, the wavelengths of the cameras, most of the cameras that we have are what we call long wave cameras. And they operate in the 8 to 14 or 8 to 15 micron range of the infrared. And in that wavelength, then glass is opaque. So we're going to see, if we want to find the temperature of the glass, then in some respects, it's probably easier just to put a thermocouple on it. But if you want to see through the glass, we can do that with a shorter wavelength camera. So what we call medium wavelength cameras operate in the around 2.5 to 5 micron range, and they will see through glass. And they're generally used more in industry for looking at high temperature things. But more often than not, we're not interested in seeing through the glass. If we're looking at windows more often, what we will find is if there's any gas leaks, which you'll find with, and you can do a very quick scan of a building and look to see if there's any seals that have failed in the double glazed units. Obviously, you can look for cold bridging, and you'll also look for air leakage around the frames or deterioration of seals, and that's going to show up very quickly with infrared. You can cover a lot of ground very quickly in that way. Sometimes with windows, we might want to modify the airflow in the building, either through the HVAC system or perhaps putting a fan in and getting a pressure differential between the outside and the inside, and then we're forcing air through the gaps and the cracks around the windows, and it's going to show up a lot easier. Yeah, thank you. Anything else? No? Thank you very much. Thank you.